right? They both can produce a root at a constant margin equal to C, and they face the demand function D of P, right? And the firms set prices. P1 and P2 simultaneously. Okay, so to keep things symmetric, the simplest possible thing I can think of is now there's, instead of one firm, two firms. Each firm chooses what's going to be its price. The firm is willing to supply as much quantity as is demanded at that price. It has no capacity constraints. Okay? No constraints. And the firms produce a homogeneous product. Homogeneous product, which implies that the firm that sets the lowest price gets all the demand. Okay, so basically, the demand that firm I gets as a function of the price of I and the price of J is going to be equal to 0 if the price of I is greater than the price of J. It's going to be equal to, let's say, half of the demand of D of P if of D of Pi, if Pi is equal to Pj, and it's equal to all of the demand of Pi if Pi is less than Pj. Okay, so this is the demand of physics. I don't set anything if my price is higher. I get all of the demand if my price is the lowest, and I get half of the demand if we happen to set the same price. So what's the Nash equilibrium of this game? Well, this is a game, right? It's a game because we have players, we have outcomes, and we have strategies. Right? What are the players in this game? The two parts. Right? What are the strategies, the prices, and what are the outcomes? It's the profits that they get with different prices. Right? The payoffs. The payoff matrix is the profits of firm 1 and firm 2 as a function of their strategies. Okay, so what's, and now that we have the game, we can say, okay, what's going to happen? What do we expect to happen if one is playing this game? In principle, we don't know what anything will happen. But to make this work, and to try to say something about this, I say, well, why don't we calculate what's the Nash equilibrium? Why don't we say, okay, that's what's going to happen? We're going to assume that the firms play the Nash equilibrium. So what's the Nash equilibrium of this game? That? All the prices are the same. It depends. And why do the prices not be the same? The prices are the same, is saying that we have a symmetric. The firms are symmetric. It makes sense to start by searching for symmetric equilibrium. Yes, but it doesn't have to. I mean, sometimes you can have everything is symmetric, and the equilibrium asymmetric, and there's no symmetric equilibrium.
Both firms will try to.
For example,
I think that the Nash equilibrium is where both firms, where the price of the both firms are equal to the marginal cost.
okay, when the
Because
price,
they're gonna fight in order to capture all the wealth or the
Okay.
profits.
okay, so you're saying the Nash equilibrium is both firms selling price equal marginal cost.
Yeah.
Okay, and because the firms are going to fight
Mm.
to capture
All the market.
the whole market.
Yeah, because like with the lower price, you get the demand of the other one if the other one has set a higher price. So if they keep competing, they're gonna reach the marginal cost. They're not gonna put a price below marginal cost because it's not gonna result in profits.
Okay, they're not going to put a price below marginal cost because then, even if they get all of the demand,
It's a loss.
they will lose money. And so that's like, you don't want to sell as much as possible because sometimes the price is too low. If you don't want to sell at a price that's so low that you actually lose money if you're selling, right? At least not in a static gain. You could think, well, maybe I want to sell at a very low price to drive out my competitors and then I recoup the money in the future, right? But at least if we're playing this game just once, I'm not gonna sell at a lower price than marginal cost. Okay, so that's clear. I don't wanna make negative, I'd rather make zero. So it's not gonna be a Nash equilibrium because it cannot be the one that maximum. First of all, what's the definition of Nash equilibrium? Let's see if you remember from Marcus's class.
It's a strategy set where both players can deviate. Like if they deviate, they're worse off.
Okay, it's a pair of strategies in this
Mhm.
case, or strategy set in general, such that each player's strategy is maximizing their payoff function conditional
On the other players.
on
possible
the
results.
on the strategies of the other
Mhm.
players. So it's like if this player expects the other players to play the Nash equilibrium, then it's optimal for this player to play the Nash equilibrium too, right? And that has to be true for all the players. Okay, that's clear to everyone? Okay, so basically, it cannot be a Nash equilibrium to have price below marginal cost because it cannot be an optimum, right? Because I would make more profits by selling a higher price and making zero and getting no demand, but at least I don't lose money, right? Zero is more than a negative number, than negative profits. What if I set a price, but also price equal marginal cost gives me profits of zero? So it's also not amazing. So I might try to make a positive profits by selling a price above marginal cost. So why is that not a Nash equilibrium?
Because the moment you do that, the demand shifts to the other firm, right? To the other firm's firm. It's gonna be lower, or at least that's how it's being taken.
If I do that, if the other firm has a price, if I'm setting a price higher than the other firm, if the other firm has a price of marginal cost, if I set a price that's higher, I don't sell anything, so I also make zero, right? So it's not strictly worse. So basically, setting price equal marginal cost is not strictly better than setting price equal marginal cost, but it's the same. It cannot be better. If I expect the other one to play price equal marginal cost, I can also play price equal marginal cost or price above marginal cost. It doesn't matter, but in particular, I can do price equal marginal cost. It's an optimum, it's a not strict optimum, right? Because the others are also zero. Right? If I say price twice marginal cost, I also make zero. It's not strictly better than that, but it's also not worse. Okay? So it is like a non-unique maximum for me if I expect you to play price equal marginal cost. Okay, so that proves that it is an equilibrium, right? So basically, P1 equal P2 equal C is an equilibrium. But it doesn't prove that nothing else is an equilibrium. I mean, you could say, well, maybe there are Nash equilibria in which both firms are pricing above marginal cost, and they make a positive profit. Can I rule out that possibility?
No.
I can't rule it out.
Technically, if you expect the other person, like, no matter which price the other person sets, you can, like, if you set a price that is marginal cost or higher than marginal cost, still you're making profit, although I don't know
So, I mean, we've proven that it is a nice equilibrium
marginal cost.
for both.
for both.
If I expect the other
Yeah.
to price at marginal cost, it's also optimal for me to price at marginal cost, among many other things that I could do, but that's one of my optimal prices, right? I definitely don't want to price below marginal cost. But it may also be true that if I expect the other player to price above marginal cost, it's optimal for me to maybe match their price,
Or put it
and it's
just-
optimal for the other player to match my price, so that could also be a nice equilibrium.
Yeah, the problem is that there is an option that is better for you, which is lowering the price a little bit.
The problem is there's an option that could be even better for you, right? It would be okay for you to match the other person's price, right? You'll be fine. You divided the market in two, and you have a positive margin, so now you're making positive profits. It's better for you than this match equilibrium, and both are doing better. But what's the problem?
That if you, for example, have a, like, let's say C is 5, you put a price of 9, I can put a price of 8.5 and I'm gonna let all the market.
Both have a price of 9, but now I put a price of 8.99,
I get market.
and I get the whole market, so that's kind of like double my profits compared to setting the price of 9 where I get half the market.
But that would be if it's a sequential thing. This is not a sequential thing, this is static.
No, I'm not talking about sequential.
Because if one sets one price and then I do another thing, this is a simultaneous game.
So that we're meaning that, for example, if I expect the other person to set the price of 9, if I expect it, I can set the price to 8.99 and say, hey, I expect to get all the
But there's
arcade.
a chance there's a chance that strategy, if you consider all of the strategies of the other players, there's a chance that strategy won't pay off as well as that strategy. Like with that strategy, you're always better off. Because if the other one has a higher price, you get all the demand even though it's zero profits. But like, yeah, that's it.
With pricing per marginal cost, I'm not always better off, because if I expect him to have a price of 9 and my marginal cost is 5, and setting a price of 5 is not the best that I can do. I could set a price of 9 and it would be better, because at a price of 5 I make zero profits. At a price of 9 I get half the market. At a profit of $4 per unit.
But you could also expect that he expects you to do the same.
So what's gonna betray the
Well,
other?
if we both expect each other to play 9 and we play 9, it's better than playing 5. But the problem is I'm not gonna play 9.
Neither am I.
We could be playing 9, but then it's better for me to play 8.99 if he expects me to play 9. If I play 8.99, then he wants to play 8.98, right? And then I play 8.97 and so on. Until we undercut each other
Until we play 5.
until we play 5. So it's not an equilibrium to play 9.9. You see what I mean? It's not an equilibrium because I would want to deviate if I expect him to play 9, and he would want to deviate if he expects me to play 9.
Yeah, if you play anything higher than the marginal cost, the other person has an incentive to deviate.
Then the other person, yes, they can undercut you,
Yeah.
right? So if we try to coordinate on a price of 9, we meet, we do a conspiracy, and we're gonna put 9, right? Then we're like, yeah, we go home, and I'm like, ha, this idiot thinks I'm gonna put 9, so I'm gonna put 8.99. Hey, 8.99 is the same, right? I mean, I didn't cheat in the conspiracy. It's like, of course it's 8.99, not 9. Everybody puts like 8.99. That's just like psychology. And then I get all the market, and he gets 0 because he put a price of 9. Right? But then you are like, ha, I know he's gonna play 8.99, so I'm gonna put 8.98. right, and so on, and our whole conspiracy unravels, right? You see what I mean? So basically, you can write the best response functions here, and it's like, if this is like the price of from 2, let's say, and this is the price of from 1, then, and here's the marginal cost, right, from 2 and the marginal cost from 1, it's like, I'm never gonna price below marginal cost. So if I expect from 2 to price below marginal cost, I'm gonna put price equal marginal cost. But if I expect him to price higher than marginal cost, right, then I'm going to price like just below the price of the other layer, right? So from 1, the price just below the price of from 2. So it's going to be like a 45-degree line, but just slightly below, right? This is the best response of layer 1 as a function of the price of 2. And then the best response of 2 as a function of P1 is the same, but like a mirror image of this. So it looks like this. It's like marginal cost here, right? If layer 1 is below marginal cost, layer 2 is going to choose a price that's equal to marginal cost. But then if layer 1 is pricing above marginal cost, layer 2 is going to have a price that is like right below the that of layer 1, right? And so the mass equilibrium is the intersection of these two best response functions, okay, which is here. That's the unique Nash equilibrium. And all of these, even though they're very close to the Nash equilibrium, they're almost touching. Those lines, those best response functions are not actually touching. I don't know now it's clear like this is this best response, right? I'm gonna do this one in like 2 lines. So this one is the this one is like okay, so this is called the Bertrand paradox. Okay, why is it called the Bertrand paradox? Because basically, it's kind of puzzling that going from 1 firm to 2 firms gets you from like the monopoly outcome to the perfectly competitive outcome. So it's like then you have like, it's like you have the market structure and you have like how many firms do you have in the market? 1, monopoly. 2, perfect competition. 3, perfect competition. 4, perfect competition. 5, 1,000, perfect competition. It's like it doesn't matter how many firms you have as long as there's more than 1. And that's because in this particular game, the competition is so intense, it's so tough, that it very quickly converges to a competitive outcome. Okay, because you have price competition, which is in generally speaking, not always, but like most of the time tougher than quantitative competition. And you have thought of as being like tougher than quantitative competition. And homogeneous products, so there's no product differentiation. And the firms have the same costs. So there's nothing to compete on, and they're both fighting for the market very directly on prices. So it's just very, competition is very tough. I mean, that's what we were trying to And what would happen if the costs were asymmetric? So if firm 1 had a cost C1 that were lower than firm 2. So what if C1 is less than C2? So asymmetric costs. Then they would also undercut each other, but firm 2 cannot undercut firm 1 below C2. Right? So in the end, firm 1 doesn't have to go all the way to C1 with the price. It's going to set price equal to C2
A little less.
minus epsilon, a little less, right? Just below C2. So if C2, if your cost is 6 and my cost is 5, I'm going to price at 5.99, right? Then you're out. I have a monopoly with the price of 5.99. Okay? Then the Nash equilibrium is P1 equals to C2 minus epsilon, and P2 equals whatever, anything greater than C2.
What is this there? No, anything.
What is it? Epsilon.
No.
Anything, yeah.
Anything. So that's one possible answer to the root paradox is if there's asymmetric costs, then it's not the same. It's not exactly the same. There's going to be some positive profits in equilibrium, but that's also true in perfect competition. That firms with lower costs have positive profits. Another possibility is that there's uncertainty about the cost. So you don't know what the cost of your competitor is. And the book has an example of that. It's kind of nice. It's technically a little bit more complicated. And this is then you have to solve like a differential equation. To do it, you have like a continuum. No, you have two firms, but they have like some idea of the distribution of the cost of the other firm, and they know their cost, which is drawn from the distribution, and you can calculate the equilibrium. And it's kind of interesting. It's like one page in the book. Maybe we'll do it next class. I've never done it in class, but it's a possible alternative to random products. If they don't know what the cost of the other from us is, then there is some markup in the group. And the more firms you will have, the lower the markup is going to be. An alternative is quantity competition. So quantity competition softens competition compared to price competition, as we will see. Basically, oligopoly, and it's like the other classic 19th century oligopoly model. Oligopoly with competition in orbits. Also called Alain Bourneau, 1838. Okay, so this one is like even older. Actually, I think Bourneau introduced this model in a book. I think it was called Mathematical Psychics or something. I'm not sure. Yeah, it's like kind of like mathematics, but maybe that was Edgeworth. I forgot what the name of the Bourneau book was, but Bourneau wrote a book like a long time ago, and it had both the first mathematical expression of the monopoly model that we saw, and the first oligopoly model, and maybe the first economic model that had a Nash equilibrium before Nash. Right, so this was like kind of crazy that he did it, like so early. Before game theory was really developed, this guy was kind of intuitively doing the Nash equilibrium. I'm pretty sure people before that have done Nash equilibria when thinking about games, like probably thousands of years. It's not like the first Nash equilibrium ever. I'm sure there must be some kind of like informal kind of reasoning that people have done for Nash equilibrium, because it's just so intuitive, right?
Like the
It's
one in the bar.
like what?
Like the one in the bar from the movie.
Like the one from the movie. I don't know if that's actually a Nash equilibrium. Let's see in the bar from the movie. No, but for example, like kids playing rock, paper, scissors,
Yeah, oh.
right? If you're playing rock, paper, scissors, I guess that game rock, paper, scissors probably goes back like at least 50,000 years.
Not just a point.
and I don't know, and the kids were playing rock, paper, scissors, like, and I'm sure they were thinking, well, what's the Nash equilibrium of rock, paper, scissors? Is I have to randomize the three, because otherwise the other player can guess what I'm going to do and we can respond accordingly. I play maybe more of the thing that beats the one that I'm playing, right? So intuitively, it's a very simple Nash equilibrium in mixed strategies, right? But I think like a lot of kids kind of intuitively get. You see what I mean? So it's not like who knows the virtual Nash equilibrium. I'm sure that people playing simple games like tic-tac-toe or something like that were like already knew how to play tic-tac-toe and it was a Nash equilibrium. You see what I mean? And they probably thought about it almost in those terms, right? Because you're trying to solve the game in your head. And tic-tac-toe is a game that basically intuitively you can solve almost fully. Actually, there's a book called Tic-Tac-Toe that has like the pages, all the possible combinations of things you can play with tic-tac-toe. So you can play, and it tells you if you play this, go to this page. On each thing, you're like, the book plays a thing, and then it says in square which page you're supposed to go to if you play that square. You see what I mean? So you have all the possible combinations of tic-tac-toe. And tic-tac-toe is small enough that you can basically write out all the possible game tree for tic-tac-toe. In chess, you have right, there's too many possible combinations of chess to be able to do it. But in tic-tac-toe you can, and in rock, paper, scissors also you can like solve the game in your heads. Here Cournot solved the game of quantity competition with two firms. So duopoly, two firms, but now the firms, instead of choosing prices, they choose quantities, and now we're going to say linear demands. We don't have to do linear demands. Linear demands, or linear demand. P of Q equals A minus B times Q. And firms and constant market cost equal to C for both firms. And firms choose Q1 and Q2 simultaneously. Okay, so this one, in a way, is easier because in this one we're not gonna solve for the Nash equilibrium this kind of like cutesy like story or like undercutting and like reasoning kind of as a story kind of way. We're gonna solve it by doing maximization of profits of from one, maximization of profits of from two, because the objective function here is continuous. In the Bertrand one is in a way it's a bit more difficult, and we have to do this kind of like reasoning and kind of more logic based. Because in this one, the profit function is discontinuous. So you cannot just do like max profits choosing P. Why is it discontinuous? Because the demand function was discontinuous, right? If I set a price just one cent lower, suddenly I get double the market, right? That introduces a discontinuity in the demand function and by extension in the profit function. You see what I mean? That's why actually it's harder. This one. It's hard, but in the end, it's easy enough. And in a way, it's easier because you can just talk about it. So I don't know if it's easier or harder. But it's definitely not like apply brute force and just mathematics and solve for the Nash equilibrium algebraically. So it's more like think about it and you'll figure it out, right? So you need less math, but you need to think more. You see what I mean? With Cournot, the objective function is continuous because the function, this function is continuous, Q is equal to Q1 plus Q2. And that's going to be a continuous function, your inverse demand function. If I increase my quantity a little bit, the price is going to go down a little bit. It's not like suddenly if I increase quantity by by 1 unit, the price goes down half, right, and just jumps up. So I don't have any discontinuity. So you know discontinuity. Non-continuous payoff functions. Then I can use the same math that I was applying to Monopoly, but now to find the best response functions. Instead of just like LP. So now firm I is going to maximize its profits as a function of QI and the quantity of the other firm, choosing its own quantity and taking the other firm's quantity as given, right? So it's given the other firm's quantity, I want to know what's my best response. Okay, and the profits are going to be P of QI plus QJ, right? The investment function evaluated the total quantity that the firms bring to the market times QI times the units I sell minus C times QI. And remember that this is A minus B times the quantity, so this is going to be A minus B times QI plus QJ. And I here could be, if I'm from I is my quantity, and J is the other firms. B times QI plus QJ minus C, all of these times QI. Okay, this is the price that I get per unit minus the cost is my margin in dollars. My margin times my quantity is my profit. Okay, my dollar margin times how many units I sell tells me how much money I made in total across all units.
But in the formula expressed like that, isn't it A minus B times QI in parentheses QI plus QA minus CQI, because they're assuming QI multiplies that.
Well, I taken the QI out as
Yeah,
common factor. This is my margin cost, and C times QI is the total cost. So this is like per unit price minus cost. Times units. So now, first order condition with respect to QI is the derivative of this with respect to QI. It's A minus B minus BQJ minus C, and there's one times this.
Means BQJ.
And so far you've done A times QI, that's A. You've done minus BQJ QI, so minus BQJ, minus CQI, minus C. And now you're missing minus B QI
B2.
squared,
Means B2, yeah.
minus 2 B QI, right? And from this one, I can basically solve for QI, right? And that gives me the best response. So therefore, basically QI is equal to A C over 2B, right? And this is the best response function. Okay, and maybe we could plot the best response, right? We can say, okay, depending on what from J does, what does from I? So let's say from J is from 2, and from I is from 1, right? And let's see if we can plot this. We have Q2 and Q1. Q1 is A minus B Q2 minus C over 2.
It's a downward slope, downward Q2 produces.
Now it's going to be downward sloping, right? Before they were upward sloping, those responses. And if Qj is equal to 0, if Q2 is 0, how much does Q from 1 produce?
The whole market.
It serves the whole market. It's going to balance money, it's going to produce like A minus 0 minus C over 2B, right? So it's A minus C over 2B. Q1 is going to be A minus C over 2B. And then the slope of this is 1/2. 1/2. Right? Because it's minus B over 2B. The slope with respect to Q2. So the slope here is minus 1/2. So here is something like this. And here, this would be twice this, right? So it's going to be A minus C over B. Because I'm going to the slope of 1 minus 1/2, so it's going like, it's going to double when I go all the way here, right?
A minus C over B. Is that
A minus C over B. If I'm thinking about this correctly. And now, we can also do the best response of the other program, put them together and get the Nash equilibrium. Then we didn't do the second order condition, but within the bands and constant marginal cost, we say the monopoly case it always holds, it's also going to hold in the Cournot case. Right? We should also take second order condition there to check that it's a maximum.
And by symmetry, we can say Qj is the same by replacing Qj with Qi, right?
Yeah, exactly. By symmetry, we have 2, the other 2, right? So basically, we're going to have like a symmetric right now, in which like something like this, right? It's like 1/2. This is the best response, let me call it like R1 of Q2, right? Q2, and this tells me like the Q1 as function of Q2, and then we have like the best response of 2 with respect to Q1, right? And this is the best response is A minus B Q2 minus C over 2B. And here we have A minus B Q1 minus C over 2. Except this, of course, is thinking of it as a function, like this is a function of this, the axis of it. Right. So now I have these two best responses. The Nash equilibrium is going to be in this point. Q2 Cournot and the Q1 Cournot are made at the intersection of the two best response functions. let's say, okay, suppose that I expect from 2 to produce nothing, right? If I start here and say, okay, let's say from 1 doesn't expect from 2 to produce anything, it's gonna say, okay, then I'm going to produce this much, right? I'm gonna go here because that's the best response of from 1. Okay, but then if from 2 expects from 1 to produce here, the best response of from 2 is here, right? So now from 2 is going to produce this much. So then from 1, if it keeps this kind of like chain of reasoning, it says, okay, then actually from 2 is not going to produce nothing. It's going to produce this because it's going to expect that I'm going to produce this, and so it's going to respond by producing this amount. Then the best response of from 1 is to produce this amount, right? But then the best response of from 2 is to produce here, right? And then the best response of from 1 to that is to produce here, and then all the way until you converge to a Nash equilibrium. Okay, this implies that the Nash equilibrium is stable. So if you start away from the equilibrium, kind of like the chain of reasoning gets you back to the Nash equilibrium. And same on the other side, right? If you start like here, you come like okay. So basically you go towards the Nash equilibrium. I thought you had questions. Okay, what else can we do with this model? Any questions so far? I think we could do a couple of things. We could solve for it for the Nash equilibrium algebraically. I mean, so far we just say, okay, what's the idea? And how do we solve for it algebraically? We put the 2 first order conditions together and we solve the system of 2 by 2. Or we put the 2 best responses, which are just an algebraic transformation of the first order condition. Like solving for your quantity as a function of the quantity of the other. So, I mean, I guess, yeah, why don't we do that? We can also do comparative statics. So you could say, okay, we could make the model asymmetric and say, this is the cost of from 2 and this is the cost of from 1, right? And this usually is the cost of from I. Let's say they don't have symmetric costs, the costs could be asymmetric, Ci and Cj, and here you will have the cost. Right, so it will be Ci. So the costs are asymmetric here. You could say, okay, suppose that the best response function are asymmetric now, and we could say, okay, what if the cost of firm 1 decreases?
Then Q1 is going to be higher.
Then Q1 is going to be higher, right? Because the best response with the higher cost, because the cost is subtracting here, right? Remember this is A minus C1 over 2B, right? If C1 goes down, then A minus C1 goes up, right? So it shifts, the slope is still 1/2, minus 1/2, right? So then my slope goes up. Let me do it in like a different graph. Well, we could do it in the same graph. My cost goes up, my cost goes down, my best response shifts up, right? And now the new Nash equilibrium is not this anymore, now it's this one, right? So now I'm going to go to the no equilibrium. New Nash equilibrium, and the new Nash equilibrium has higher quantity for from 1 and lower quantity for from 2.
Okay. Can we find elasticities with the phenomenon?
Can we find the elasticities of demand?
Yeah, we could do log of QI and the log of QJ. We make like a type of log model and we can see the exchangeability of our product.
But they're the same.
Well, here they're homogeneous products. Both are having the same product. You could calculate what's the elasticity of demand, the inverse elasticity of demand. We'll do it. That's a
It would
point.
be the same for both.
Sorry?
It would be the same for both, right? They will have the same demand.
In the symmetric case, it would be the same for both. In the asymmetric case, it wouldn't.
Right.
Necessarily the same for both. We'll see. There's interesting stuff to say there. Okay, we're good on time now. Okay, so that's the 2x2 case of the Kuna model. Now we can do it with n firms instead of 2. So n firm case. State linear and constant marginal cost. So how do we do this with n firms? Let's see if we can do it in the 23 minutes that we have left. Okay, so n firms and asymmetric costs. So now from I, now basically Q is equal to the sum from I equal 1 to n of Qi, right? The overall quantity is the sum of the quantities across all the n firms instead of just 2. And we can define Q minus I equal to the sum for j different from I of Qj, right? It's the sum across all the firms excluding from I. So we call that Q minus I. So we can also say Q total quantity is Qi, the focal firm, plus Q minus I. Right? It's two different ways of writing the same thing. So I can write it as the sum across all, or I can write it as these firms plus everybody else's. So now let's say firm I maximizes its profits, choosing Qi. Now you'll see why that's useful. So now I can write it as A minus B times Qi plus Q minus I minus C I times Qi. Okay, this is the price as a function of the total quantity, which I write as Qi plus Q minus I for firm I, minus the cost of firm I, that's the profit per unit, times the number of units that firm I chooses to produce. Okay, and then I take first order condition of this. First order condition of this, with respect to Qi, looks exactly the same as that, except instead of Q2, or instead of Qj, now I have Q minus I, because it's not just one other firm that I go J, it's like the quantity of all the other firms put together, except for me, Q minus I. So it's going to look exactly the same. You see what I mean? So it's basically A minus 2B Qi minus B Q minus I minus C equals 0. Now the best response function, best response is Qi equals A minus 2B, sorry, minus B Q minus I minus Ci over 2B. Okay, just same as before, instead of qj, q minus I. But now, solving for the system of equations for this is not as simple as solving the system of equations of 2H. Actually, we can solve the system of equations of 2H. But that one we can do, it's 2H. You replace the best response of firm I or firm 1 in firm 2, and you're done. But here you can't really do it.
No, but the same logic applies, right? Where firm 1 and firm 2 intersect in an n-dimensional space, everyone has to intersect, right?
The same logic applies. Basically, the solution is this. I mean, I have a first order condition for each firm. I have n firms. I have n quantities. It's a system of n by n, first order conditions. The solution of the system of equations given by the first order conditions of n by n, an n times n linear system, is the Nash equilibrium. Okay, and linear systems of n by n, then I can solve them like on the computer, right? With Python or something like that. But solving it manually, like in closed form, is not so trivial. But in this case, it can be done. So there's a trick to do it.
Wait, we're supposed to win.
No.
Oh, okay.
You could do it, maybe, but maybe it will take you like, I don't know, a couple of days. Depending on how it's practiced. Maybe you can do it in 5 minutes, maybe you can do it in 2 days, I don't know. No, doesn't matter. It's a trick we have to learn it. It's like, this is not like problem solving Olympiads. I mean, it's good to problem solve. But I don't know, it's like, I'll show you the trick, it's in the book. It's not that tricky either. I mean, it's just like writing it down with patience and thinking of it. So let's write that system of equations. Let's see what it looks like and let's see how it could be solved. So, okay, so we have the first order condition. So we're not going to operate on the best responses. We're going to operate on the first order conditions. Okay, so first order condition of firm I. Let's try to write it like yeah, now I remember the trick. Okay, the trick is true. Is to sum across all the firm's first order conditions.
To sum the what?
To sum across all the first order conditions of all the firms. See, it's not that crazy. So you could have thought of this yourselves. So we have n firms. Each of them has a first order condition. Now we sum them. Okay. So what happens if you sum across all the first order conditions of all the firms? So we have to do like the sum of I equal 1 to n. Sorry guys, I really didn't remember. It was there somewhere. Okay, so it's the sum of A. What's the first order condition? A minus 2B QR minus B Q minus I minus CI, right? Equals 0. Sum of 0 is 0. And then we have the sum of the first order condition. So if each first order condition is equal to 0, then the sum must also be equal to 0. Right? And then if we sum A, the sum from I equal 1 to n of A is A times n. So this is A times the sum of minus 2b qi is minus 2b times the sum of qi, which is q, right? It's the iterative quantity. And now the sum of minus b times q minus I
NQ minus Q
is nq minus q.
N minus 1.
Because q minus I is q minus qi. Right, so this is going to be, let's just write this one as q minus qi, right? So this is going to be n times q minus q. You see what I mean? So this is going to be minus b times n minus 1 times q, right? But let's just write it like n minus q minus q, right? And this is n minus 1 times q. Minus, and here there's no trick, unfortunately, minus the sum of ci. Equal 0. Okay, so now we can solve for q, for the overall quantity. And if we have q, then that's going to give us q, and it's going to give us a lot of systems that we can solve for qi as a function of q, basically because we have a qi and q minus I. Q minus I is qi is q minus qi, so then we can solve for qi as a function of the q that we're going to have here. You see what I mean? So we first solve for the q, now here the sum of the things, so it's going to be 8n, 8 times n minus sum of ci equal to b times 2 plus n minus 1 times q. Right? I'm passing everything that has q to the other side, and I'm going to have b in both. So b comes out, and here I have a 2 with a plus now, and here I'm going to have n minus 1 with a plus. Right? So it's 2 plus n minus 1. And of course, all of these have q, which I also take out. So I have q, b, and now instead of having 2, I have 2 plus n minus 1. Well, actually, before I can have 2. Okay, 2 plus n minus 1 is n plus 1. So q, no, equals n times n minus the sum of ci from I equal 1 to n divided by b
That's NCI, no?
times n plus 1.
The sum from I to N, from 1 to N of CIs, isn't that N times CI?
It's n times the average of ci.
Because not all firms may have the same cost.
None of them are the same cost, but they're asymmetric costs. But yeah, you could think of that as n times the average. I like to think of it that way. The book doesn't do it that way because then the algebra gets, it actually complicates the algebra to think of it as the average, but I think it's nice to think about it like the average. But let's keep it together for now. Let's not call it like, I would like to, yeah, we could call this thing like C bar of n, where C bar is equal to the sum of Ci over the average. Okay, so we have the overall Q, and now we need to solve for the individual Q's, right? So Qi, in the best response, we said is equal to, best response is A minus B over minus B times Q minus I. That Q minus I is just Q minus Qi minus ci over 2. So now we have to bring the qi, solve for qi as a function of q, and we got it. So we need to bring qi to this side. Qi is times b minus minus over b, so it cancels out, times 1/2 basically. Right? So this is going to be qi times 1 minus 1/2. So this half. So in the end the qi kind of goes away, and I'll just get rid of this 2, right? Qi equals a minus ci over d minus minus 1/2 of q. Gonna be plus 2 minus maybe. I think so. Okay, so then I have a q here, and I just have to replace this q here and over it. Sorry, I don't know this by heart. Equals a minus ci over b minus a times n minus the sum of ci over b times n plus 1 times 2, right, because of this 1/2. Now can we combine them? I think we can. Right, because here we have a times n, right? This we have to multiply and divide by n times 1. So we have a times n plus 1 minus times n plus 1 times 2. So we have a over 2b n plus 1. We have to multiply these times n plus 1 times 2. A times n plus 1 times 2 minus a times n. This is going to be n plus 1 times 2 minus n. So 2n plus 2 minus n.
What is QC, Jose? It's the total quantity of the core model.
QC is the total quantity.
Sí, no oculta.
Produced in total. A minus b times q minus qi minus ci over 2b. That's correct. Then here I kind of maybe got. No, I think it's right, but that's not the best way to do it. Look, I'm just gonna write it this way. let's first solve for QI here, which is what we do, which is A minus CI. Let's get this 2B here again, 2B QI. So it's 2B QI. Plus DQI on this side, D. Plus here we put it here with a minus, so it's BQI. Here it's something wrong. BQI, right? 2BQI minus BQI is BQI on this side. BQI equals A minus BQ minus CI. Right, so what we really want is QI equals A minus BQ A minus CI over B. So actually I think I had done it wrong. I think I had done something wrong before because I put the half here, but I actually have crossed out the half, not. Okay, sorry, I made a mistake. Shameful. Okay, this is right.
Yes.
Okay, so QI is this, and now QI for no is going to be this with Q for no. Now we can put this formula here after simplifying, and it will simplify. We'll get something that's in terms of A, CI, and C minus I, which is like the sum. We can define C minus I equals the sum for J different from CJ. And we can basically have like an expression that's going to depend on those reasons. We can do it. I mean, now it's not going to be that hard. Okay, so this is going to be A times n plus 1. I'm going to multiply this times n plus 1. So now we just have, before I will confuse and I was putting half here, but it's really b times n plus 1 and b times nothing. So to get common denominator, we have to do b times n plus 1, right? So everything here, we have to multiply times n plus 1. Divided by b times n plus 1, right? So now I have a times n plus 1 from here minus a times n. Right, so a times n plus 1 minus a times n. Now it's nice. Okay, now it's nice. So now it's just a, right? A times n plus 1 minus a times n. Now it's just a. Now minus ci, right? Times n plus 1. Plus the sum of ci and c minus i times nothing, right? So it's plus ci plus c minus i, which is the sum of all the ci's of all the other terms. And plus ci is just minus ci times n plus 1, it's just going to be ci times n here. And here we have plus c minus I times down. And that's it. That's it. It wasn't so bad. Okay? So that's the Nash equilibrium. In the case of n firms with asymmetric costs. And I guess it's so. So those are basically the main two classical oligopoly models: price competition and value competition. This is going to be the building block of everything we do, right? Basically, if you know these two models and you know how to solve these two models and apply them in different situations, you pass the course. Now we're going to do different models that are like variations of these models, and applications of these models to things like mergers and cartels and so on. But these models are going to show up over and over and over again. Everything is either a variation or a build on these two models. Okay? So next class we're going to talk about we're going to start talking about we're going to say a couple more things about Cournot that we will solve for the model, and then we need to do a few more things with Cournot. And then we're going to talk about dynamic oligopoly models, so entry and sequential competition. Okay, so we have to say the firms don't play simultaneously, or if the firms are, because here we say, okay, there's n firms, or why are there n firms? And do more firms want to enter the market with these profits, with these quantities, or not do some firms want to exit the market? I don't know. So, okay. Questions, comments, complaints? I'm the director of MEF, so if you want to complain, I'm the guy. Okay? Complaints over here.
Bye bye.
Careful with what you do.
Jose,